Imagine throwing $500 million directly into a trash bin. That is exactly what Elon Musk did when he canceled the production of the most advanced carbon fiber rocket in history. Why would the world's most successful engineer abandon high-tech aerospace materials to build a Starship out of the same stuff as your kitchen sink? Today, we reveal the secret of the stainless steel revolution and why this mistake is actually the only way to reach Mars. For decades, the golden rule of space travel was simple: lighter is better. Every single gram saved meant more fuel, more cargo, or more distance. That's why carbon fiber was considered the holy grail of rocket science. It's ultra-strong, incredibly light, and it looks like the future. SpaceX spent years and hundreds of millions of dollars developing massive carbon fiber tanks and specialized million-dollar robots to weave them. They were building the Interplanetary Transport System, a black, sleek composite beast that looked like it belonged in a Hollywood blockbuster. At that time, carbon fiber was the only logical choice for a Mars-bound ship, or so we thought. But in late 2018, everything changed. Deep in the blistering heat of South Texas, workers started welding massive sheets of shiny, heavy metal. The world laughed. Critics and aerospace veterans called it a water tower that would never fly. It looked like a relic from a 1950s sci-fi film, not a modern spacecraft. The move to 301 series stainless steel seemed like a massive step backward. Steel is heavy. Steel is old-fashioned. On paper, it was an engineering disaster. The aerospace community was stunned. Why would Musk throw away years of research for a material used to make pots and pans? Musk realized something the rest of the industry had missed. He wasn't just building a rocket. He was building a logistics machine that had to survive the hellfire of atmospheric re-entry over and over again. You see, carbon fiber has a glass ceiling. It melts and loses its structural integrity at just 200 degrees Celsius. To survive the 1600-degree heat of re-entry, a carbon ship needs a massive, heavy, and fragile heat shield. But steel? Steel is different. It's cheap, it's durable, and it thrives where other materials burn. When you are building a fleet to colonize a planet, the high-tech choice can quickly become your greatest liability.
To understand why carbon fiber failed, you have to look at how it's made. It's not just a material, it's a high-stakes manufacturing nightmare. Imagine you are building a rocket that is 50 meters tall. To make it out of carbon fiber, you need a giant pressurized oven called an autoclave. You have to weave thousands of layers of fiber with surgical precision and then bake the entire structure at high temperatures. For a ship the size of Starship, SpaceX would have needed to build the largest autoclave in human history. It was a slow, incredibly expensive process that left zero room for error. One tiny bubble in the resin, and the whole multi-million-dollar section is scrap. Then there is the sheer cost. Carbon fiber is the diamond of the aerospace world, costing anywhere from $100 to $200 per kilogram. When you are building a fleet of hundreds of ships, the math simply doesn't work. Elon Musk looked at the numbers and then looked at stainless steel. The price? Just $3 per kilogram. It was a difference of nearly 60-fold. But it wasn't just about the money, it was about speed. While other companies were spending months weaving a single composite tank, SpaceX workers were out in the Texas wind welding steel sheets together in weeks. But as an engineer, Musk knew the real secret of steel was hidden in the temperature. Most materials have a fatal flaw. When they get extremely cold, they become brittle and shatter like glass. This is a massive problem for rockets filled with supercooled liquid oxygen and methane. Carbon fiber struggles in the extreme cold of space, but stainless steel 301 is a freak of nature. Instead of becoming brittle, it actually gets tougher and more ductile at cryogenic temperatures. It becomes stronger the colder it gets. This was the ultimate engineering cheat code. By switching to steel, SpaceX gained a material that was 60 times cheaper, significantly faster to build with, and naturally suited for the frozen reality of deep space. The world saw a shiny water tower, but Musk saw a ship that could be mass-produced like a car. However, there was still one massive hurdle. Steel is heavy. Everyone in the industry knew that a steel rocket would be too heavy to ever reach orbit with a meaningful payload. To
To solve this, SpaceX had to reinvent the very concept of how a spaceship survives the most dangerous part of any mission, the return home.
Now, let's address the elephant in the room. If steel is so great, why isn't everyone using it? The answer is simple: weight. In the world of rocket science, mass is the enemy. On paper, a carbon fiber ship is significantly lighter than a steel one. For decades, engineers believed that a steel spaceship would be a heavy brick that could never get off the ground. But this is where the genius of the steel revolution truly shines. When a rocket returns from space, it hits the atmosphere at 25 times the speed of sound. The friction creates a plasma furnace that reaches 1600 degrees Celsius. Carbon fiber, as we mentioned, begins to fail at just 200 degrees. To keep it from melting, you have to cover the entire ship in a thick, heavy, and extremely fragile thermal protection system. These tiles are a nightmare to maintain. Just ask anyone who worked on the space shuttle. But stainless steel can handle much higher temperatures. Because the steel shell itself acts as a structural heat shield, SpaceX could use much thinner and lighter thermal tiles only on the most critical areas. When you add up the weight of a carbon ship plus its massive heat shield and compare it to a steel ship with a minimal one, a shocking reality emerges. The steel ship is actually lighter. This was the breakthrough that silenced the critics. While the rest of the world was still running computer simulations, Elon Musk's team was building the Starhopper, a crude, three-legged steel bucket in the middle of a Texas field. It didn't look like a spaceship. It looked like a high-tech grain silo. In July 2019, as the Raptor engine roared to life, the water tower didn't just sit there. It hovered. It flew. It proved that a cheap, shiny metal could do what everyone said was impossible. But the true test was still to come. Flying a small hopper is one thing. Surviving the belly flop, a maneuver so dangerous it had never been attempted in history, is another.
The belly flop maneuver was the final piece of the puzzle. Watching a 16-story metal tower fall sideways through the clouds, only to ignite its engines and flip upright at the last second, changed everything. It wasn't just a spectacle, it was proof that steel could handle the dynamic stress that would have shattered other materials. Elon Musk's gamble had paid off. Today, Starship stands as the largest and most powerful flying object ever built by human hands. It is a monument to a simple yet profound engineering truth. Sometimes, to move forward, you have to look backward. By choosing the humble 301 stainless steel, SpaceX didn't just save $500 million. They gained the ability to iterate, to fail fast, and to build a production line that could eventually launch thousands of ships to another planet. This journey from high-tech carbon fiber to pot and pan steel teaches us that the best solution isn't always the most expensive one. It's the one that actually works under the most extreme conditions. As we watch these silver giants leave our atmosphere, we are witnessing a new era of logistics, one where the cost of reaching the stars is finally falling within reach. But here is the real question for you. Now that you know why Starship is made of kitchen-grade steel, would you trust your life to this shiny giant on a 6-month journey to Mars? Or do you think the carbon fiber era will eventually make a comeback? Tell us in the comments, a simple steel or carbon is enough. And if this deep dive into the engineering of the future was worth your time, hit that subscribe button. Stay tuned to WWW channel, where we break down the complex machinery of our world. See you in the next one.